Hello, this is week 2's lecture. It's about chapter 3, the distributions and SPC process. And this lecture is part 1. It covers from slide 1 to slide 62. And the rest of the slides will be in part 2 video. So in this lecture, we will first review the definition of quality we talked about in chapter 1 and 2. Then we'll learn some visual data displays. When do we use them, the advantage and drawbacks of them. Then we review some basic statistics we learned in Statistics 1, which is the prerequisite of this course. Next, the most important part is introducing some important continuous and discrete distributions and examples. When do we use them? And get to know what is central limit theorem. Quality has many definitions: better performance, better service, or better value, or whatever the customer says it is. But in the context of SPC, quality has specific meanings: understanding of process variation, control of process variation, and improve of process variation. So let's first review some statistics or measurements that help us understand process variation. If we use the probability distribution function, PDF, to view them, where the horizontal axis represents the value of a random variable x, and the vertical axis represents the density of the probability. People usually focus on 3 aspects: location, spread, and shape. The basic statistics should reflect the quantity and how it communicates information. Let's review those statistics. First, mode. Mode is the value or values that occurs most frequently in a distribution. As with discrete distributions, there may be more than one mode. Here is how we identify mode. Then median. Median is the value separating the higher half from the lower half of a data sample. It is thought as the middle value of a data set. Here is how we compute the median. The mean is the average value of a data set. It is found by adding all values and dividing by the number of values. Mode, median, and mean reflect the location of distribution. As to spread, first measure is range. We use R to denote it. It is the difference between the biggest and smallest values of a data set. Range is easy to calculate, but sensitive to outliers. So we can use variance to remove some of the outliers' impact. We use sigma square to represent the entire population's variance, and we use S square to represent the sample variance. For process, we may or may not know sigma square, but we can usually obtain a sample from the whole population and compute the S square and use it to estimate sigma square. This is how we calculate sample variation. The good things about variance is that, unlike the range, variance measures the dispersion with less emphasis on outliers. However, the units of variance is the square of the unit of the variable, so it does not make much sense, and it is hard to compute. The equation is complicated. Therefore, sometimes we use standard deviation instead of variance. Standard deviation is the square root of variance, so its unit is the same as the unit of variable. Again, we use sigma to represent the standard deviation of the whole population, and we use S as the sample standard deviation. The equation either looks like this on the left or looks like this on the right. The denominator is n minus 1, not n. because the definition of standard deviation or variance indicates that there should be at least two observations in a sample. That makes it meaningful to care about the spread of the sample. If there is only one observation, then the standard deviation should be undefined. Here is how we deduce the equation on the left to the equation on the right. Why do we do this? Because if we need to compute a standard deviation manually, we prefer to use the one on the right because it is relatively simpler. The third aspect of a distribution is shape. We use PDF, the probability distribution function, to visualize the potential variable value mapped with its likelihood. For normally distributed random variable x, its PDF looks like this. The area under the curve from one value to another shows the probability of getting an observation in between the two values. The total area is 1 or 100%. If we use the mean mu and standard deviation sigma to divide the PDF, mu plus and minus 1 sigma covers 68.26% of the total area. Mu plus and minus 2 sigma covers 95.46%, and mu plus and minus 3 sigmas covers 99.73% of the total area. Next, let's look at several ways to display a data set and get a visual idea of the location, spread, and shape. The first one is stem and leaf display. The definitions are in the textbook, so in the lecture, let's directly talk about examples. Given a data set, the cycle time to pay employee health insurance claims, there are 40 observations in this data set, from claim 1 to claim 40. The cycle time unit is days. The claims range from 16 to 56. To make a stem and leaf display, we first divide all observations into several bins, which means subranges. In this case, we write the 10 digit into the middle column, which is the stem, and write the single digit into the right column, which is the leaf. The first item is, the first bin is from 15 to 19, so we write 1 here on the first row. There is 116 and 2 17ths in this bin. So we write 677 here on the right. And the second stem is from 20 to 24, so we write 2 in the stem column, and then there are 322s, 322s, 123, and then 124. So we write 22234 on the leaf column corresponding with in the second row, so on and so forth. Then we count how many observations in each bin and write the cumulated number into the left of each row. There are 3 observations in the first bin, 16, 17, and 17. So we write 3 here. In the second bin, there are 5 observations, 22, 22, 22, 23, and 24. So the cumulated number is 3 plus 5, which is 8. So we write 8 here. So on and so forth until to the middle range, or one line above the middle range. Then we start from the last row. Do the same thing. Write the cumulated counts number upward to the middle range. which is 35 to 39 here. Here for the bin 30 to 34, we write 8 here because 8 is the number of this single bin. And we can either use 8 to add with 13 to add up, to add downward, or use 19 to add 8 to add up upward. It depends. Anyway, 8 is right in the middle, so we use it. So we use so it so we use it to be in the parentheses to indicate it is in the middle. And if it's previous been at this number, it will be another value. We observe that the shape of the stem and leaf display is a bell shape laying down. It means the cycle time to pay employee health insurance claims follow a roughly normal distribution. Most employees' health insurance claims cycle are from 30 to 40 days, which is this range. And this range, these two bins. The benefits of using stem and leaf include it immediately deliver the important features of the data by giving a visual impression of its shape, spread, or variability and central tendency. Here are videos of creating a stem and leaf plot using Excel and Minitab. We can also use a time series plot and use dots to show the stem and leaf, like this. Another powerful method to display data's features is histogram. Suppose we have 100 semiconductor wafers. We measure their layer thickness. Similar to stem and leaf, we group all observations into bins, then count the number of observations in each bin and plot the frequency or relative frequency of the observations. Relative frequency means when all the numbers are super large and the differences are not obvious, then we can cut off a certain chunk of each number so that the difference between the numbers can be highlighted. So for the data set, if we group them into 10 bins, we will have a histogram like this. It roughly shows the shape of the data. It is near normal distributed, but a little right skewed. Here are the videos to create a histogram using Excel and Minitab. Another similar tool is cumulative frequency plot. Instead of showing the counts in each bin, it shows the accumulated counts from the first bin to the current one. From this plot, we can tell the increasing speed. In which bin the frequency increases fast and in which bin the acceleration stops. So this helps us take advantage of the marginal effect. Using the histogram, we can easily calculate the proportion of observations that fall into a certain range, like this. You can pause the video and read in details. So benefits of using histogram include, it is a more compact summary of data. It visualizes data effectively when the data set is large. It's more effective than using the stem and leaf. And it is easy to observe its shape, spread, variability, and the central tendency by using bars. Box plot is another tool that delivers key messages of a data set. By showing a lot of measures, it displays the max value the third quartile, the mean, the max, the median, as many as you can. And in some tools like Excel or Minitab, it automatically highlights the outliers using dots, and all the value inside this box is not considered as outliers. We may use comparative box plots to compare several data sets. It quickly gives us the idea of the relative location, spread, and shape by comparing multiple data sets. Box plot can display several important features of a data set all at once. That is the benefit of using it. We need to choose the right tool to summarize and visualize the features of our data based on the dataset's nature, utility, and what we want to know. Next, let's move on to another topic of today's lecture, describing variation. The data visualization tools such as stem and leaf plot, histogram, and box plot are used to describe sample data. A sample is a collection of measurements selected from a population. Sometimes we use a mathematical model to describe the value of the variable with the probability of occurrence in the population, and such mathematical model is called probability distribution. Probability distribution can help us describe, predict, and improve the quality of a process through a series of actions. Find the special causes, head of shifts in process, obtain predictable output, continuously improve the process. So what should we know about distributions? What do we do, and why do we care about distributions? Distributions quantify the probability of an event. For example, a normal distribution, events near the mean are most likely to occur, whereas events far away from the mean are less likely to occur. Any normal distribution with a mean of mu and standard deviation as sigma can be converted into a standard normal distribution, which has a 0 as its mean and 1 as its standard deviation. When we convert it to a standard normal distribution, we can use z-table to easily look up the probability of an event. We can have a single interpretation of sigma of normal distribution. We can use how many sigmas away from the mean to know the probability of a variable value. So this is 1 sigma, 2 sigma, and 3 sigma. Standard normal distribution's mean is 0 and standard deviation is 1. When we convert a normal distribution to a standard normal distribution, we use x to subtract mu divided by sigma, so we get the z value. We use phi z to represent the probability of obtaining a value no greater than z or less than or equal to z. In other words, the area under the curve from negative infinity to z. Because standard normal distribution is a symmetry about the mean 0, phi negative z equals 1 subtract phi z. Here's an example of how we use the z-table to look up a probability. How likely do we observe a data point more than 2.57 in a standard normal distribution? It is the area under the curve from 2.57 to positive infinity. We can get the value by using 1 to subtract the probability of phi 2.57. How do we use the table? In the z-table, if we know the z value and look for the probability of phi z, we read z from the x, like this, 2.5, and 7, 2.57. Then so the probability phi z is in the middle. However, if we know the probability phi z and want to look up the z value, we can read the table inversely. Pay attention, the probability is less than or equal to a value or greater than or equal to a value, which determines if we need to use phi z or one subject phi z. Also, if z value is a negative value, then we can use 1 minus phi negative z to obtain phi z. Next topic, let's learn or review some important discrete and continuous distributions. When the variable is on a continuous scale, its distribution is a continuous distribution. The metal layer thickness is a continuous distribution. Then the parameter can only take on certain discrete. When the parameter can only take on certain discrete values, its probability distribution is a discrete distribution. For example, the number of nonconformities or defects in a printed circuit board. To calculate the probability of a range of outcome is to calculate the area under the PDF. For continuous distribution, we use integral to calculate the area. For discrete distribution, we add up the area of each bar. We add up the value of each bar. A discrete distribution example is rolling dice. If we roll 2 6-sided dice and look at the sum can be from 2 to 12. The most likely outcome is 7. There are altogether 36 combinations, among which 6 combinations gives 7. 6 over 36 is 0.167. So that's the probability of getting a 7 when we roll 2 6-sided dice. We can visualize all the outcomes using a histogram and then use it to calculate the probability of obtaining a certain outcome or the range of outcomes. Like this. If we roll only 1 dice, the probability of obtaining any number from 1 to 6 is 0.167. It's like a uniform distribution, but it's discrete. If we roll 2 dice and use the sum, the probability of getting a 7 is the highest, which is the mean, median, and the mode of all the outcomes. The further the outcome is away from 7, the lower its probability is. It's very close to a normal distribution. This is central limit theorem, CLT. In many situations, when independent random variables are summed up, their properly normalized sum tends toward a normal distribution, even if the original variable themselves are not normally distributed. Now let's look at a continuous distribution example. Suppose that X is a random variable that represents the actual contents in ounces of a 1-pound bag of coffee beans. The probability distribution of X is summed to be Fx equals 1 over 1.5, where X is ranged from 15.5 to 17. This is a continuous distribution since the range of X is the interval from 15.5 to 17. This distribution is called the uniform distribution, and it is known graphically. It is shown graphically in the textbook figure 3.10. Note that the area under the function Fx corresponds to probability, so that the probability of a bag containing less than 16 ounces is when we calculate the integral of Fx from 15.5 to 16. So the result is 1/3. we have learned that the mean of a probability distribution. So if we want to know the probability of a bag less than certain number, then we can use the integral to calculate the area under the PDF. We have learned that the mean of a probability distribution is a measure of the central tendency or its location. The mean is calculated in different ways for continuous and discrete distribution. For continuous distribution, the mean is the integral of variable multiply the probability distribution function for the whole range of the variable. For discrete distribution, the mean is summing up the variable multiply the PDF for all values, all outcomes of the variable. However, the mean may not equal to the median or the mode for some distributions other than normal distribution. For example, when the distribution is skewed or has multiple modes. As an important statistic that measures the scatter, spread, or variability in a distribution, variance is also calculated in different forms. For continuous distribution, its variance is the integral of the square of variable subtracts the mean multiply the PDF, the whole range of the variable. For the discrete distribution, its variance is the sum of the square of every outcome, subtract the mean, then multiply the PDF. Another statistic, standard deviation, is the square root of variance, so its unit is the same as the variable. Now let's get familiar with several discrete distributions. How can we calculate their means, probability, and variance, and then how can we use them? First, the hypergeometric distribution. Here are the equations for the probability, mean, and variance calculation. The hypergeometric distribution is for selecting a random sample of n items without replacement from capital N items, among which D, the capital D, are non-conforming items. A random sample means all possible samples have an equal chance of being chosen. Let's look at an example. Suppose that a lot contains 100 items, 5 of which do not conform to requirements. If 10 items are selected at random without replacement, then the probability of finding one or fewer non-conforming items is like this. So finding one or fewer non-conforming items include two situations, either finding 0 non-conforming item or finding 1 non-conforming item. So we sum up the probability of both situations. In this example, the capital N is 100 and D is 5. In the lowercase n, the sample size is 10, and X is either 0 or 1, and we need to sum them up. So we plug in the value, we get this probability. If we use Minitab to compute the probability, it uses capital M instead of capital D as the number of non-conforming items. Here, it lists the probability of getting X or getting X number or fewer number of non-conforming items. As we increase X from 0 to 10, reducing D, or we observe that the probability increases, and it increases as 1 when it reaches 5, because D is 5 over 100. So reducing defect rate, the D is the key here. Here are two other examples on slide 53 and 54. You may pause the video and read them. So when should we use hypergeometric distribution? As a discrete distribution, it is used when we want to determine of obtaining the probability of obtaining a certain number of successes without replacement from a specific sample size. The certain number is x. The specific sample size is lowercase n. Usually, when x is relatively large and lowercase n is relatively small, we tend to use hypergeometric distribution. The second discrete distribution we use quite often is the binomial distribution. Here are the equations to calculate the probability, the mean and standard deviation of a binomial distribution. The random variable x is the number of successes out of n Bernoulli trials with constant probability of success p on each trial. Binomial is the appropriate model for sampling from an infinitely large population or large enough population, where p, the lowercase p, represents the fraction of non-conforming items in the population. X represents the number of non-conforming items found in a random sample of n items. For example, here is an example. If p equals 0.1 and n is 15, then the probability of obtaining x non-conforming items is, we use the equation like this. So as we set x from 0 to 10, we can obtain the probability. Here we list all of them. We list the probability of x as we increase x from 0 to 10. What if we change the fraction of non-conforming rate p or the sample size n? How will the probability change? On the left histogram, we fix the sample size n as 15 and set p as 0.1, 0.5, and 0.9 respectively. We observe that the shape of the distribution changes as p increases. As p-value increases, it is more likely to get more non-conforming items. The mode divided by n is close to p. On the right, we fix p-value as 0.25 and increase n from 10 to 20 to 40. As n increases, it is more likely to get more non-conforming items as well. Again, that's because the mode over n is close to p. This is easy to interpret. In a large population where the non-conforming fraction p is known as a constant value, when we randomly select a sample with size n, the non-conforming rate of the sample, x over n, should be very close to p. Some examples of binomial distribution: tossing a coin 100 times to see how many land on heads. P is 0.5 for most types of coins. Asking 100 people if they have ever been to Paris. Rolling 2 dice to see if you get a double. When do we use binomial distribution? We usually use it to find the probability of getting a certain number of successes, but there are some requirements when we use it. There are fixed number of trials. Each trial is an independent event, which means the probability remains constant from trial to trial. That's why we use it in the population that is infinitely large. Otherwise, as we select the samples, the probability may change. And there should be only two outcomes, like a Bernoulli distribution. Like Bernoulli trial. We can also use observations to calculate the whole population, which is to use x over n to estimate p. We use p hat to represent estimated p. Here, the x is a binomial distribution with parameters n and p. Often p hat is the ratio of observed number of defective or non-conforming items in a sample x to the sample size n. And this is usually called the sample fraction defective or sample fraction non-conforming. The hat symbol is used to indicate that p hat is an estimate of the true. So in this way, for a very large population where we cannot get the real value of p, we can use the p hat to estimate the p value. That's the meaning of doing this sampling as an estimation. You may have observed that there are similarities and differences between hypergeometric distribution and binomial distribution. So here is a question for you to think by yourself and summarize the commonalities and differences between the two observations. For Deming's red bead experiment, when calculating the probability of a certain number of red beads in a batch, what distribution should we use? What distribution should we use if we only have 500 bees? And what distribution should we use if we have 5,000 bees? Think about it. And that's all for part 1 of the lecture. And part 2 of the lecture will be uploaded tomorrow on Thursday.